My name is Michael Hennerich. I'm an embedded systems architect at Analog Devices in Munich. And today I want to briefly introduce some open source HDL IP and software components for building leading edge software-defined radios. So we all kind of know this. You can use commercial off-the-shelf SDR modules until a certain point. You could even like ship a USRP or something like that in a product, but many people go beyond the point and they create full custom hardware, and that often involves FPGAs. So it's kind of the last prototype production step. Also, some customers I've seen actually skip the commercial off-the-shelf SDR phase and directly move to an FPGA carrier board with some FMC add-on hardware. So over the years that we're doing this, we have been trying to come up with a single cohesive solution that meets people in their ecosystem and tools of choice. So we kind of developed this I/O infrastructure with a mind that can be used in GNU Radio, can be also used in MATLAB Simulink or in Python, and people can choose the environment that they want to be in there. I think we also talked a lot about I/O. I don't want to really talk about I/O today. I actually want to focus on that programmable logic part, since I think we haven't really talked too much about that in the last years. So I want to do this a little bit. So the common architecture makes it really easy to transition between platforms, since our reference designs, our open source reference designs, they are all built on the same stack and technology and infrastructure. So you could go from an ADA and Pluto to a 6 giga sample multi-channel RF digitizer without actually relearning anything. And even the HDL IP cores, the transport layer core, it's exactly the same. It has the same register map, uses the same Linux driver, and things like that. So everything is open source and publicly available for all these reference designs. This is what we envision a typical prototype system can look like. It's typically either an AMD Xilinx or an Intel Altera FPGA carrier board together with an FMC card that either we provide or any of our third parties make those cards as well. And we support typical FPGA carriers. For example, we wouldn't support a low-cost set board with a gigasample ADC because it just doesn't have the compute or interface capabilities. We provide full-stack HDL designs. We call them reference designs. They all use the common HDL and I/O infrastructure. We typically terminate to DMA via AXI stream or FIFO type interfaces, runs across different FPGA vendors, Intel, AMD. We also design them in mind that you can actually insert your custom processing block inside the design without like redoing everything. So this is not really RF knock where things is on the fly and you can do this. This is more like you know what you do. You generate the processing logic and then you insert it into the design and you resynthesize it, build the bit stream, and then you can have potentially different bit streams that are being loaded for different configurations. We also support industry standard tools, AMD ILAs, Intel Signal Taps, MathWorks, HDL Verifier, and so forth. So these reference designs are being made out of discrete HDL blocks, and we design and support interface logics for various of our ICs, encapsulating any and all obscure designs to provide a common, easy to understand and consistent interface that's portable across commonly available FPGA devices and standard cell libraries. Oh, that was a long block. I think a few bullets here. Again, it's all open source, it's documented. It's typically Verilog source files and Intel constraints files. We test them to the latest versions of the tools. So all these FPGA vendors, they have like at least 2 releases a year. We try to follow those. They are tested and proven. They're modular, easy to use, scale, debug, and customize. So when we do those cores, we make them really configurable. So if there is a feature in the core that you don't need in your product, but would like it during development or debug, you can just disable it, and the software driver will read a capability map from the HDL core register map and enable or disable the feature. So you don't need 10 different software configurations, it's always just one driver. This is a small excerpt of our HDL IP library. We have more than 80 different IP cores for all kinds of different things. You even see a lot of like IP cores for precision converters that are not really subject for any SDR. They have 24 bits. They can sample up to 2 mega samples, but the interface is so complicated that you cannot really attach it to a standard processor over SPI. Even through on a data sheet, you find SPI. But it's a SPI that needs to run at 200 megahertz, make only to like 12 bits per sample and things like that. There are other things like system utilities. XE fan control is an IP block that automatically queries some system ADCs and turns the fan on or off based on parameters. XE clock gen, for example, wraps around the standard MMCMs on these FPGAs and gives them an AXI configuration interface so they can really change the frequency from a Linux driver instead of loading a different bit stream or using a DRP interface to do so. Many of these blocks are kind of like that. Then there's also the IC-specific IPs. I have an example here. John Graf talked about Navasa, our ADRV 9002. Of course, we also have an IP block for that. You can see it on the right. It kind of follows always the same split in physical layer, data link layer, transport layer, and they're all software enabled. For a lot of the high-speed converters, as soon as you go beyond 100, 200 megahertz, you always end up having a kind of a JES-D2-4 type interface. There are some well-defined layers, file layer, link layer, transport layer. And we have IP cores to handle all of them. A while ago, I talked about the JES-D interface framework. It's basically a system-level integrated HDL software framework that covers the entire link setup, configuration, procedure, manage the different components in the system, and makes those interfaces really easy to use. So, but I want to focus on some of the IP layers. I'm going to do that from physical to transport to application layer, bottom up. So the physical layer, its primary purpose is to take care about the transfer of bits to and from the data converter to the FPGA. It's used to control and configure the low-level primitives on these FPGAs. Handles the physical medium, serialization, deserialization, for example, the high-speed transceivers and their PLLs, clock and data recovery. But the whole thing is really very, very FPGA specific. And while it is so FPGA specific, we kind of created a common HDL IP core around those very specific transceivers that you can find on the next slide on these different FPGAs and give them a consistent look and feel to the software. That's done through an AXI4 memory mapped interface. The core typically handles the reset sequence and the sequencing for many things, and the reset sequence on those physical or on those transceivers is actually quite essential. We also add reconfiguration capabilities so that you can change the PLL, CPLL, QPLL kind of things on the fly. You get status information, whether it has logged, whether there's a buffer overflow and underflow. This is all stuff that you wouldn't typically need to solve somehow in your HDL, and there's no real software interface provided by anyone. I'm aware of. We also added statistical iScan capabilities. So for example, the Xilinx transceivers has that. That can always run in the back. You just kick it off. You can always have your physical running without interruptions, and you can capture periodically a bitmap that kind of shows an eye diagram. And the supported transceiver families can be found on that slide. So that's TTX, TTH, TTH3 and 4, TTY, Warsaw, and on the Intel side, Area 10, Stratix 10, LH Tile, Agilex, and so on. And these transceiver families are really quite different, and we support them with a single IP and with a driver that handles them. The data link layer is specific to the JEST-204 communication, implements 8B10B or 6466B encoding, implements support for synchronization of multiple lanes and multiple devices, has diagnostic capabilities and runtime reconfiguration support. The transmit layer IP as well as the receive layer IP, both are subclass 0, subclass 1, deterministic latency, has diagnostics, multi-link support, and what's kind of important is it has much lower latency compared to any other JEST IPs that are out there. Same thing for the transmit layer 1. Give me a second. There's also interrupt support. For example, if one of the lane goes out of sync, you get an interrupt and you can act accordingly. The transport layer. The transport layer takes the data from the physical layer or the data link layer and splits it into channel-specific streams. The streams may include one or more samples on the same clock, and depending on the specific part, we might have additional features just like PRBS monitoring, per channel data formatting, DDS, pattern generation. There's even like a small IQ correction block that you can enable with a matrix multiplier. Like I just said, the transport layer IP core has PRBS generator and the DDS dual tone DDS feature, while the ADC transport layer has the PRBS checker implemented. Yes, I talked about the signal processing logic, the placeholder. It's the big donut hole where you can add your custom processing logic. It has a FIFO-like interface with data and valid, and it's right now shown between the TPL and the CPAC core, but if the per channel operation is required, you can actually also move it after the CPAC core. In some systems, we also see this where it kind of stops after the transport layer or after the pack because streaming into memory is not required. They just implement their custom logic and it just stops for us here. Some of the system utilities that we use besides the three layers, there is the CPAC and the UPAC core, and what it basically does. So typically the physical interface captures data continuously for the maximum number of channels the system is configured at boot. And the IP, the PAC or the unpack IP are meant to allow one or more channels to be enabled by software without any padding, allowing full usage of the DMA bandwidth without any overhead. For example, if you have enabled 16 channels, you're running out of memory bandwidth over the medium or over the transport medium or in the storage. You just disable 15 of them, and you only have like one channel, and now your bandwidth bottleneck is gone. Of course, you have much less channels, but these cores do this on the fly. And there are kind of independent IPs, but they're getting controlled through the transport layer. So the transport layer, if you have a channel enable, it's just an output and it goes to an input on that core. The data offload engine. That is an interesting one. If the bandwidth of the data coming from the FPGA or the stream toward the device is higher than the capability of the memory interface, we need an additional FIFO. Sometimes this FIFO is implemented in the FPGA memory using BRAM, for example, and sometimes we use an additional DDR that is exclusively used for this purpose. On some of the FPGA carrier, there's dedicated DDR memory that is not really the system memory for your processing system. You can implement a DDR controller in the fabric and then use this DDR memory that is not used by anyone else, and you can just really high throughput stream in that with the full theoretical memory bandwidth capabilities the DDR has on the datasheet almost. But in essence, the offload engine is a clock domain crossing store and forward buffer with some extra features useful for bursty applications. It was specifically designed to sit between the DMA and the DAC for the TX side and between the ADC and the DMA on the RX path. Some of the features, it's configurable, how big the FIFO is going to be like, how much of your VRAM is allocated for that FIFO. You have an AXI interface. You can also bypass it. So, for example, if you now reduced kind of the number of channels, the bandwidth is smaller, and you couldn't use the regular DMA, you can just bypass it. It has also support for cyclic operation and store and forward operation. So cyclic is kind of a thing where you put a waveform into the memory and just have it repeated over and over again. The AXI DMA-C. So DMA is a crucial piece of the system allowing transfer of data to and from the memory at very high bandwidths. Our core supports also the cyclic functionality and supports multiple interface types, AXI3, AXI4 memory mapped, AXI4 streaming, and FIFO interfaces. And kind of the reason why we kind of reinvented the wheel was that any of the DMA engines or cores that were available with the standard tools, libraries, were not good enough to keep up with the really high bandwidth and the streaming requirements we had. And this is sometimes multiple gigasamples per second. And some of the other AXI DMA cores are more designed for like packetized, bursty data, and you will see underflow or overflows depending on the direction if you don't use the AXI DMA-C. Recently, we also added scatter gather support now for it. The driver for all this is also mainline. So I'm almost at the end of my talk today. I want to give some news and updates. First on the kind of the Linux I/O infrastructure. So over the last 1.5 years, we tried to mainline most of our high bandwidth DMA infrastructure in the I/O core. On the analog devices kernel, we implemented the MEMAP interface, which we never mainlined. And the idea was to replace it with a DMA buff interface. And that is now a mainline. So DMA buff allows zero copy of buffers between where they are generated and where they are consumed, manipulated. And you can also re-enqueue it into the kernel and stream it out USB, for example. So we also added the DMA import interface for the USB gadget framework. With that, we can now saturate basically every medium or every transport that we find today. We also added I/O backend support for complex aggregate devices. Those are typically converter devices where you have like two interfaces on them. One to configure the converter, that's typically a SPI or an I2C interface, and then you have a data interface. And the data interface is kind of abstracted by kind of an AXI core that is a kind of a platform device. And then you always had the problem that you have like a SPI device and a platform device, and how do they communicate and how do they interact with each other, and that solves that in a very nice manner. libIO version 1 is to release very soon. I think 2 years ago, Paul talked about it in Washington. It was almost also, no, by that, DMA buff support was just an idea. He went through multiple cycles to actually push it through on the Linux kernel. But it is now all good, and it will release soon. And a TRIO libIO patch has already been submitted. It's a bit early, it's a draft PR, but once we release libIO version 1, it should come soon. The other thing that I wanted to talk a little bit about, I found it really interesting, is the cache coherent transactions or the cache coherent interconnect on some of the newer SoCs, ARM quad-core SoC types. They really boost. So while we benchmark libIO and the new protocol and everything, we figured out, hey, we spent the majority of the time not in the drivers, not in the library, not in user space. We spent them in cache management. So it was like going each page 4 kilobytes at the time, executing code, waiting until the flash is succeeded or the invalidate. And by just having this being done automatically by the hardware, we see significant 3x boost. So where we've done like 50 megasamples before, it was all of a sudden 150 megasamples over USB. Or where we maybe did like 60 megabytes on gigabit Ethernet, it was all of a sudden fully saturating gigabit Ethernet. And the CPU utilization dropped by more than 50%. So even like this, without the libIO version 1, is a really worthwhile thing that you could try out on some of the bigger, newer ARM FPGA SoCs. Yes, some references. Everything's open source. It's either on Wiki, .com. We are moving some of the documentation, especially related to the repositories, into the repositories, render them with swings, and load them up to GitHub IO pages. So they are always in sync this way, and we don't have the documentation on the wiki, which is out of sync with the source code you find on the repository. And while we're doing this, you may see some inconvenience that because something disappears here and appears on the other side, and so it's always good to take a look at GitHub pages as well as wiki.analog.com. So that's the end of my talk, and it's getting close for the social today. I thank you for listening, and see you later.